integraltypen står här någonstans. All right.
Sorry, we need to introduce you. Sorry, all your horses. So, welcome everyone to the Monday seminar today. We have two presentations today. First one is Christian Jakobsson, who will be presenting his master's thesis. He has been advised and supervised by Pekka. And afterwards, we will hear a conference presentation from me, but later on that later. But all right, Christian, the floor is yours. Thank you.
Normally, when we think of mathematics success in the university setting, we only think of our effort, which is the thing that defines what grades we get and how well we do in the courses. But what there are things at play which we might not notice very often, and things that are outside of your control, such as your sex, your birth month, the year you completed the course in, and other things like this. And it's these factors that we're going to analyze, how they are affecting and have affected the mathematics grades in the people in Aalto University. So 6 different questions. We're kind of aiming high and firing wide. We're looking at a lot of different things here. But for one, so the first thing is relative age. So your age compared to in the same age group. So in the same born usually from January to December. So how does this affect your mathematics grades? There has been some studies in Sweden as well as Turkey, also some looking at the PISA results, but these are mostly concentrated on lower levels, not so much on a university setting. Next thing is, with 6 differences related to mathematics, very, very conflicting results, and none really agree conclusively that we have arrived something. And same thing here, we have the problem of not having a university level studies. Next one, now we're kind of in the Finnish realm. So the impact of international students' mathematics in a university setting. There are several studies which have looked at the impact of, for example, immigrant-born students versus Finnish-born students when looking at PISA and other results. But none so far which looked at universal level where we compare elite students with Finnish students. Right. Next thing, grade inflation. So how is it easier now to get better grades than it was before? Abroad in the United States, this is the case. Mean GPAs have on average been rising 0.1 at a rate at 0.1 per decade. In Finland, there have been some studies on the lower levels. For example, in elementary school, the number of 10s, the highest grades, 3 times as common, for example, than 20 years ago. And teachers are also very, very reluctant to fail students. But how is it in the university level in Finland has not been researched yet. Also, pandemic disease, when we went to distance teaching, 2020-2021. Some studies, but not many, how these affected grades. And finally, what no one has so far talked about and researched is, when looking at mathematics grades, actually incorporating failed grades into the analysis. None so far, and we've done a very thorough literature review. None have looked at this so far. Okay, the data at their disposal, we have mathematics grades on introductory and advanced courses from Aalto University on an 11-year time frame, 2014 to 2024. We have differential calculus 1 and 2. We have probability and statistics, matrix algebra. I assume everyone in this room has completed all of these. And from the advanced courses, we have linear algebra, statistical inference, and Fourier analysis. Within the actual Excel that we got, we have the grades, of course, 1 through 5, and failing grades, the new component we're introducing. And for the explanatory variables, we have birth month, sex, nationality, different schools within Aalto University, course completion year. But note, we would have liked more data points, but we're actually constrained by the GDPR. So I actually requested some more courses, but these were the courses that, given these explanatory variables, where we could still hide student anonymity, where it kind of had a large enough sample size. Right. So here, kind of to get a feel for the data, take a well look at this one. Then the grade distribution, you see we have quite a lot of failed grades, and then kind of going a little bit up, we have 1s, 2s, 3s, 4s, and most number of 5s. But given that we have categorical data, we can't quite apply the normal linear regression things that you would normally have. So we have a problem, which is that the distance between the grades might not be linear. What that means, for example, with the failed grades, we don't know quite where the threshold is. What's the level of difficulty from going to a failed grade to a 1? Or for that matter, going from a 1 to a 2, 2 to a 3, 3 to a 4, 4 to a 5. All the courses have kind of different groupings where you put the thresholds, so we might not allow to look at this from a traditional regression viewpoint, so we're going to do something else instead. And the solution is we take odds ratios. So we know, instead of looking at the numerical values per se, we instead look at the probabilities of the different categories. And we do this with the odds ratio. What the odds ratio does is it simply divides the ratio of being in a high category compared to a lower one. So it's simply saying that how many times is this divided by this? Simple as it gets. Next thing we do is we take the logarithm of the odds ratio. And why we do this, before we had an exponentially, this one on the left, your left, and an exponentially rising curve there, but when we take a logarithm, it's going to be easier to fit a regression line there, as we'll see later. So now we can fit now a standard regression model. And notice we don't do this to the data itself, to the grades themselves, but actually the probability distributions of the grades. And if you do some algebra, you can, probabilities you derive, showing this one straight from the model there on top. So what about then our explanatory variables? What are these? So we have different variables. We have sex as a binary, we have Finnish or international students, which is also binary, we have birth month, 1 through 12, January through December, grade completion year, 2014 to 2024. So how do we create a model? So what we do with the variables is we transform them into binaries with a baseline category, and then introduce the variables to get the individual effects, introduce them one by one in the model. So what our baseline is going to be, and I'll show shortly why we do this, is a Finnish male student born in April through November who completed courses in 2014 to 2019 and 2023 to 2024. We also add in one additional coefficient of kind of the yearly, to measure the grade inflation, kind of the yearly, how it changed on a year-by-year basis. So our variables, we have sex, 0 for male, 1 for female, nationality, born in the first quarter, 1 if you're January through March, born in December. We have the different school variables. Then we look at COVID years 2020 and 2021, COVID 2022, grade inflation, and finally we get the model of the categorical grades compared, mapped out against all the different variables. Okay. So we take the models and we put these into the beta, yada 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 yada. And this next variable right here, that's simply to see if we can fit in a certain demographic and get the probability of that one. So this probability y given x is the probability of a given demographic. Let's say we have a female student and we have an international student. We have these two things in common. So we have a 1 for x on the female, so we introduce the beta sex. We have also 1 for the nationality, so we introduce the beta nationality into the model and go on from there. Yes. And now you remember that we introduced the baseline of, and the reason was that we want to look at the impact of the grades one by one. So how do we do that? Given that we have the following model, so what we did is we have categorical data, which we cannot fit with the traditional regression model. So we take the probabilities of these categories, make them into odds ratios, take a logarithm of that, and then to the logits of the odd ratios, we fit the standard regression one. So if we do some algebra again, raise both sides to the power of e, we get the following. But notice here now, this thing right here can be transformed into this right. This is standard exponential rules. And what this is going to mean is that if beta is larger than 0, it means that this is going to be larger than 1. And when we multiply this into the model, it's going to show us that variable bj tends to push the into a higher probability category, right? Because the ratio gets larger, so the numerator gets larger, this one gets slightly smaller. And of course the opposite if it's smaller than 0, and if it's equal to 1, no difference. So given this background, we're going to introduce two models. First one is logistical regression. Logistical regression won't have two categories. And our two categories in this case is going to be pass and fail. So we have the high category here, the low one here, and we get the following. And how to assess the logistical regression model, we have this ROC curve. And for example, if we have a model as such, let's say we have an observation where x1 is female and we have x2 is an international student also. So if we're going to classify this, we can first calculate the probability of getting a passing grade. And then onto the ROC curve, ROC plot, we either, depending on what our threshold value is, we'll either categorize this as a failing grade or as a passing grade, right? And if we were to iterate over all the different thresholds, we would get the area under the curve is highlighted, and this is the AUC value. So if it's equal to 0.5, we are as good as random chance, right? We can just guess. And if it's bigger than 0.5, sorry, then it has some predictive power, correct? So with respect to the data, we would split the data, the fail grades and the passing grades. And we're actually going to analyze this in two different ways. these represent all the basic courses. And from the plot you can see that roughly everyone who takes mathematics completes these courses, right? But everyone who completes these courses does not necessarily complete the advanced courses, right? So we're going to analyze it in two different ways. One is we're going to analyze these separately, and then we're going to analyze them all together. Because separately there's roughly 52,000 data points, and together there's over 60,000. So we have a big data set, I suppose. And now for the second model. And this one works almost the exact same way as the logistical regression model. But the thing is here now is that we have more categories than one, right? Because with the logistical regression, we only separated the passing grades and the failing grades, right? But inside here now, we're actually introducing more thresholds, and we're going to do this inside of the passing grades. So we have the following, and actually the only thing that changes is we have no more cutoff points. So this variable bj, we actually now have j minus 1 of this. But the thing is, with this proportional cumulative ordinal regression model, is although we have these different thresholds, we assume that the effect of the variables across the threshold is going to be the same. And this is called a proportional odds assumption. But this assumption has to be tested. And this can be done with the Brandt or Larkin ratio test when going to these. But if the assumption does not hold, it's not the same effect across the different categories, then we have to switch to the partial proportional odds model. And this actually happens later on. So here we have the grade distribution. Now we introduce a second cutoff point here. Same thing here. We analyze first these separately, then everything together. And ways to assess the model fit. We have the likelihood ratio tests. Then we have the R squared, which is the correlation between the model estimates and the real data, and then also this R squared called McFadden. We can get into the later one as that. And now for the results. For the logistical regression model. Only look at the two most right-hand columns here. That's where the juice is. So we have the baseline term, which remember was a male Finnish student who completed in 2019, somewhere around there. So we calculate the odds ratio, which was this estimate to the power of e to the power of the estimate. And this is the odds ratio. And with the formula that we saw before, we can calculate what the model estimates is the passing probability. And then for all of these, depending on if we have a positive or a negative, we multiply this odds ratio that we had with the intercept with e to the power of the estimate, and then we get the separate odds ratios. So what you're going to see is, for example, for the first one, is we're going to have a higher probability of passing if you're a female student. For international students, slightly lower. For these, slightly lower than if we compare them to ski. If you're gender through March, we have no statistical significance. In December, we have slightly better, but maybe the biggest find is that during 2020 to 2021, not surprising, people passed their grades way easier than before. So with the model fit, we have statistical significance, area under the curve 0.6, better than 0.5, McFadden R squared are these. For all the models, we have almost the same coefficients, not quite, but same pattern. We can get into this later in the questioning. Again, here we have the model fits. And then for the cumulative ordinal regression, when we introduced, so remember I talked about the proportional odds model, and we did the Brunt test, and if this is 0, we gotta reject those variables, and if this is larger than 0, then it might hold the proportional odds assumption. But as you can see here, is that for most of these, the p-value is going to be larger, smaller, or 0, so we actually, for most of these variables, are going to reject the proportional odds assumption, take a partial proportional odds model. So the results for these is, again, we have the reference, and again, females do a little bit better in both of these. International students do a little bit better. Generated through Marsh, no difference, no statistical significance. But again, the noticeable thing was that during the pandemic with distance teaching, it was easier to get better grades, which was not surprising given that. So, major findings, females outperform males. This was contrary to almost all the previous research. Not everything, but close to everything. During the 2020 to 2021, we had a decreasing proven. Grade inflation, it was slightly decreasing, which is surprising, but we can get into the reasons later. Also contrary to research in the United States and here in Finland. International students, slightly different. December board students perform better than your baseline, but no statistical significance for those born early in the year. And finally, some slight concern, the partial proportional modus model became slightly unstable. We had to remove the schools, which was not the interesting part of the study, to make the model stable when we compared everything to the School of Science. And we had I can get into this later as well. And a fairly low model fit values, but it's expected with large data set when there are small statistical effects to be observed across large samples. So this was one slight concern as well. Here are the sources.
Thank you. Then questions.
Yes.
All right, I have two questions. First of all, thank you for the presentation. The questions. First, you chose the logistic regression model here.
Yes.
And one aspect, I'm not an expert in the logistic regression model, but
yeah,
my understanding is still such that the parameter value by which is like more or less inputted into the model is a linear combination of the parameters and
yes,
of the attributes or categories as you have here.
Yes.
Is there a reason for why we chose a linear combination of these values, as in effectively one interpretation of choosing a linear model, or like an additive at the very least, is that, for example, gender can be in some way compensated with choosing a different school? Like, I mean,
could you open up what you mean by that?
well, you have like or gender plus school and the parameters there.
Yes.
That's your model here.
Yes.
But wouldn't it be a reasonable question to have gender and school? Effectively considering it not as an additive model, but rather as a, well, in principle it could be called a category, but you're already using the word category here, so it's not necessarily a very good explanation here. But nonetheless, the key point here being like an additive model more or less at least has an attribute where you kind of make at least an implicit assumption about some property or category being compensatable with another category.
You could, for sure, and do I understand it correctly that you would take like these two attributes together?
Yes.
Yeah. So I thought about that, and we actually thought about with Pekka as well. But the thing we thought of was that we're not quite sure like which attributes should go together. And then there's a lot of like different ways you can combine the different attributes. Do we combine two? Do we combine three? If we start doing the like different combination that we can analyze. We're quickly up in the hundreds or even thousands of different ways to look at it. So we chose like.
So the question kind of is there an inherent reasoning to why this model would be the model to choose? So pretty much the explanation kind of here is it is simple or whatever, but like is this actually how it behaves? That's kind of the real question that I'm asking.
It is. For example, if let's look at the logistical regression model once again. So you see here we have the different estimates, and you see we have different, we have both positive and negative ones. So for example, if we were to look at no point are we, like with the model, like if you remember when we multiply these together to get the estimates, right? So if we were to combine these different, we actually can, for example, combining, let's say we take the female students which have in this case, a positive coefficient, and combine the international student which has a negative one. So you're an international female student, you're gonna get slightly better grades for being female, but in this case, we have a slightly high chance of failing due to being international. So it's kind of baked into the model already.
Maybe perhaps discuss it more in depth. I have another more perhaps interesting question here.
Yes.
Have you considered, so you calculated the p-value, yes, but I don't actually really know what the p-value here is, but I will explain it nonetheless without considering the p-value here.
Yes.
Have you considered deriving, let's say, 95% confidence intervals for those estimated parameters? Effectively meaning that, so now we're kind of saying that yes, for example, female student is more important than being an international student, but that's kind of the mean estimate. If you would derive the 95% confidence interval for that parameter, we could perhaps make a more statistical result or reasoning about whether this actually is true, but it's not just effectively noise. So could we derive the, let's say, 95% confidence interval for the female student estimate here?
We could, yes.
Although the sample size is quite large, so I don't imagine that the variation would be very high, but it would be interesting to see nonetheless. Or at least I would consider it interesting, not very well.
Yeah, but do I get it wrong? But we could derive it from. Hold on. It's very easy to get these things confused.
Generally, I would say you cannot necessarily derive it directly from that unless you make an assumption about the underlying distribution. So if you assume it's normally distributed, then perhaps you could do it. But it's not necessarily normally distributed.
Yeah, I would say that's correct. Yeah. Yes.
Yeah, did you somehow divide your dataset into testing samples and training samples for your model, or did you use all the data for training the model?
Used all the data for training the model.
And these test statistics are for the same data?
Yes. Yes.
Are you or someone else going to do some further work with this, or I mean, is it just a numeric exercise, or are you actually planning to use these figures to some maybe improve?
good question. When we applied it for the data from the university, it was contingent on that we write it for the master thesis, but we're going to do a publication later on as well, which will probably come out in early fall.
And do you think you might use this to improve teaching, for instance, knowing how it sort of which factors might affect
I don't
grades?
know.
Yeah.
Let's hope so. Let's hope so.
What would you like, if you want to use it for teaching, what would be your result for teaching?
Like which aspect are you
It
looking at?
doesn't give any explicit suggestion for a teacher. Give more homework tomorrow.
Like the main one that I would probably look at, like from a teaching perspective, is like this grade inflation. Because the other things are outside of the teacher's control, right? The teacher can control who applies to the university, but what the teacher can affect is how good of grades the different students get. So this would probably be the one thing that, if I were to derive some conclusion from this, would be looking at these last three things.
Maybe one more question, and then we have to move on to the next presentation.
I'm sorry if I missed out or not, but in the starting you mentioned that nobody was taking into account like how many grades were in failed grade,
Yes,
and you took into account of that.
yes.
So what do you see, like did it significantly affect the results? Something like that, because I did not explicitly understand putting on the website. What do you could suggest, like taking into account the failed grades and all?
So, for example, there have been others who have applied this ordinal regression, cumulative ordinal regression model. Maybe it goes by many names, right? But primarily has been done not with the failing grades, but with only the passing grades. People have looked at the failing grades, for example, with simple arithmetic. What share of students are, for example, failing their classes or not? But making this into the could you actually like expand upon your question, like which aspect you want to answer?
Alright, now I think we have to move on to the next presentation, so that time is running out. But you can probably discuss after the seminar as well.
Yeah.
Let's thank Christian once more. Congratulations on completing your masters.
Thank you.